Welcome back to our ARSET training series, Advanced NASA Earth Observations and Tools for Active Fire, Smoke, and Post-Fire Monitoring. Today is part 2 of our training series. My name is Brock Blevins, a training coordinator for the ARSET program, and I'll be your host for today's training. As I mentioned in part 2, or the final part of this training series, we will have an overview of static thermal anomaly data inside firms, how to use static thermal anomaly information to identify thermal anomalies that are not likely vegetation fires, how to visualize active fire information on static graphs and interactive maps, and how to analyze active fire information using a fire count histogram. Once again, the homework is available now on the training webpage. It will be due December 3rd, and a certificate of completion will be awarded to those who attend both live sessions and complete the homework by December 3rd. And with that, let's begin part 2 of the training series, Data Analysis and Visualization. I'm very happy to introduce our guest instructors for part 2. Brad Quayle joins us from the U.S. Forest Service, where he is the lead for the Disturbance Assessment and Services program. And we also have Dylan Mendez, a senior application developer for firms. Part 2 objectives. By the end of part 2, we hope that participants will be able to recognize how static thermal anomalies associated with industrial and natural sources are identified. Use data available in firms to identify locations of routinely detected static thermal anomalies, and use Jupyter Notebooks to access and visualize firms' data. Once again, if you have any questions during today's training, you can put them in the Q&A box within WebEx at any time. At the end of this training, we'll address as many questions as we can, and then we'll post a transcript of these questions and written answers to the training webpage within a week. So let's get right to it. First demonstration by Brad will be on static thermal anomalies. In particular, his outline will show an overview of static thermal anomaly data available in firms, accessing STA data, associated data, and tools in firms, and how to use firms to highlight examples of thermal anomaly activity that are not likely vegetation fires. Over to you, Brad. Thank you.
All right, thank you. Well, today what I'm going to demonstrate is our new static thermal anomaly data that we've incorporated in firms, along with some associated data sets and tools we've included to use those data. And what you see here is a firms map of Oregon and Western Idaho. And I'm going to zoom in here to Northeast Oregon, to a little town called Durkee, Oregon. And as you can see, if I zoom into this location here, just outside of that town, there's a large excavated area with an associated area of industrial infrastructure here. And this particular area, if I turn on the fire detections, I can see I'm getting some detection activity associated with that infrastructure next to the excavation pit. Well, this area here is a cement plant, and this is a really good example of a static thermal anomaly feature, because cement plants have large kilns that they use to heat up material to make cement, and these kilns burn at very high temperatures, or have very high temperatures approaching 1500 degrees centigrade, and these features can be detected by satellites and included in active fire detection data. That's why we can see them here. If I back off a little bit here on the scale, you can see those features, and here's some other detected activity here, likely associated with a fire. But if I jump ahead 1 month to the end of July of 2024, again looking back 31 days in the active fire detection record, I have all these other fire detections that are associated with wildland fire activity that was occurring at that time. And as you can see, as those detection data fill in, I have a lot of detections, for the month of July for that cement plant we just looked at before. Now, if you're a wildland fire manager, you may that may give you pause, and you'd wonder, if you're not familiar with the area, that might be associated, that detection activity might be associated with a wildland fire. So having these static thermal anomaly features inventoried and identified allows users to identify these areas of fire detections that might be associated with industrial features or natural features that are giving off heat or thermal activity and can be detected in active fire detection products. So static thermal anomalies, what are they in the context of firms? They're basically semi-persistent or persistent sources of thermal energy that we can detect routinely in active fire detection products, but they're not vegetation fires. They're associated with industrial features or industrial activity, and in some cases they can be associated with natural features that are giving off heat, such as volcanoes and other sources of geothermal activity. And what we did in developing this static thermal anomaly feature or layer that is in firms right now is we started with year 2023 cumulative active fire detection data that was acquired by SMPP VIIRS. There's about 21 million active fire detections worldwide. And then we also included Terra and Aqua active fire detections for the same year, which was an additional 8 million. So we had about 29 million active fire detection data that we processed and analyzed and thresholded it accordingly. And we summarized those data and we identified features that we determined were static emitters of thermal energy, and we identified well over 6,300 of them, and they're represented here on this map. So the next thing I'm going to show is we're jumping to a map in firms for Western Turkey, and if you want to access the static thermal anomalies layer mask, it's under this static thermal anomalies group in firms. And you can see I have it drawn up, and they're very small features at this scale, and they're showing up in magenta. But if I change my background layer to a dark gray, they stand out a lot better. You can see them here throughout Turkey and into Greece and whatnot. We also have sources of industrial heat or industrial activity identified. Now, we didn't develop these layers in firms, but we went to authoritative sources who inventory and compile this data globally, and we've provided these data in firms for reference. So we have all types of different industrial plants and also power plants, which may be emitters of heat. And so if I turn on a couple of these layers here, you can see these are iron and steel plants, cement plants, and so forth. And if I go to the layer info for one of those layers, you get a brief description of what this layer entails, and you also have a citation, a link to get to the source data if you'd like, and also a citation for the data layer. If you have any questions about these layers, we recommend that you contact the authoritative sources for these data, because these data, again, are not developed by NASA. They come from these various sources, and we're just providing them here as a courtesy in firms for folks to have context and reference to these data. So I'm going to switch back to the image base, and I'm going to zoom in here on this town in Turkey called Horozdegici, Turkey. And I've turned on the static thermal anomalies mask in magenta there. And you can see that this area corresponds to an industrial area there on the coast. And if I turn on the fire detections for this day, I'm looking at June 26th of 2025, and I have a 1-day reach back. So we're just looking for the detections that occurred on this day. You can see that there is a fire that's burning in this forested area to the south of town. And we're also picking up thermal activity associated with this static thermal anomaly area. Well, what we've done in firms is provided the capability to filter and identify active fire detections that are associated with these static thermal anomalies layers or features, I should say. And under the static thermal anomalies group, there's a static thermal anomalies detection layer. And if I turn that on in cyan, these detections that are that correspond or that are associated with the static thermal anomalies feature will be highlighted. And basically what it's doing is features that directly intersect the static thermal anomaly area as well as are within a predefined buffer tolerance are selected. So we can see that these detections are associated with the industrial activity here, and we're picking up a little bit here that some detections that are associated with that fire, but that's due to the buffer tolerance we're using there. We try not to get too aggressive so we don't pick up detections too far outside of the static thermal anomaly feature. If I jump ahead one day, this fire started the day before, you can see again for that day on the 25th, here's all the fire activity associated with that forest fire south of the city, and these are the active fire detections associated with that static thermal anomaly feature. Just want to note here, you noticed on the previous day and today, we have some detections in this area. This is obviously of industrial origin, these active fire detections, but our static thermal anomaly feature does not extend out there and capture that. And that's because, again, for this initial prototype layer we have, we only used the year 2023 active fire detections, and so we just didn't have any detected activity in that area that met our thresholds and criteria to identify that as a static thermal anomaly. So just for little things or nuances like that for users to be aware of when they're using these static thermal anomaly features. For the next part of my demo, I'm going to jump to the Hughes fire, which was a fire that burned in Southern California in January of 2025. And what I'm looking at here is on the date of January 28th, reaching back for 1 week, all the cumulative active fire detections for MODIS and VIIRS that occurred with this fire. And as you can see here, we have a little cluster of detections here, a couple kilometers away from the fire that's associated with this excavated barren area. And what this area is here is it's a landfill area. And if I zoom in here on it a little bit and turn off the detections, you can see that area and what it looks like up close there. But I'm going to zoom back out and turn the detections back on. And if I turn on my static thermal anomalies layer, let that render there. It's a little bit slow displaying. And you can see those magenta polygon is our static thermal anomalies mass that was derived from the 2023 active fire detection data. So what is going on here is, upon doing a little bit of research in this area, this is a landfill that in 2022 basically an underground fire started there. So the garbage and the waste that's been buried there in that landfill was ignited, and the fire has been burning underground and smoldering and whatnot for the last 3 years. And this thermal activity is routinely detected by the active fire detection sources in firms. So having this information would possibly help a fire manager to know that these fire detections that are close to the the Hughes fire when it was going on, they are not associated with that incident. But as you can see, as I jump through time here, and maybe if I jump into February, well after the Hughes fire was over, we're still picking up these detections through time. So just to show you that relatively small, subtle, smoldering thermal activity that's happening there with that landfill fire is being picked up and detected. And of course, I can turn on my static thermal anomalies detections and isolate those detections with that activity if I'm interested in doing so. Okay, on this last example of working with static thermal anomaly data, we're going to focus on a natural heat source. And where I'm at right now with this map is it shows the East African Rift Valley. And you can see here we have a couple of volcanoes that are present, and where we have some active fire detections that are occurring with those volcanoes. And this area here in general is the Democratic Republic of Congo. And To identify where these volcanoes are at, if you look under the overlays layer, we have a volcano layer, and you can filter these volcanoes for what's displayed based on their most recent activity. We have here by default only those volcanoes that have been active in the last 60 years are displayed, but if I toggle it to display all of them, you can see we have all these other dormant volcanoes that have not also erupted in the past 60 years. So I'm going to toggle that back to just the ones that have been active in the last 60 years, and I'm going to zoom in on this volcano here. It's called Nyamulajra, and this is the most active volcano in Africa. And as you can see on this particular date for July 30th with a one-day reach back for the active fire detection data, we have a lot of active fire detections that are associated with the volcanic activity that's occurring on this volcano that day. And if I draw the static thermal anomalies layer and turn off my active fire detections for a moment, you can see the static thermal anomaly feature that we discerned using the 2023 active fire detection data is pretty large. It extends about 3 to 4 kilometers from the main crater of the volcano. And if I turn my detections back on from MODIS and VIIRS for this day, both the day and night detections, and if I turn on my static thermal anomalies detections, I can easily filter and identify those active fire detections that are associated with the static thermal anomaly feature. But I'm going to turn that off for a moment, and also the static thermal anomalies mask, and I'm going to turn off all of the active fire detection layers except for the NOAA 21 VIIRS data for that day, and I'm also going to turn off the nighttime detection, so we're just looking at the daytime detections associated with the volcanic activity. And if I turn off the volcano layer here so you can see it a little bit easier, you can see these are the detections right here on the volcano itself. That we got some activity there, but we also have some activity here off the west slope, as well as trending down the east slope of the volcano. So if I look at the NOAA 21 VIIRS false color composite imagery on this day and turn off my active fire detections for a moment. Again, this is relatively coarse resolution imagery at this scale, but you can see with the shortwave infrared response, we have some thermal activity going on here, and faintly you can see some thermal activity out here far on the west slope as well. I'm going to turn my VIIRS active fire detection back on, and also turn off my VIIRS imagery, and I'm going to take a look at the HLS imagery. And it happens on this particular day, July 30th, both Landsat and Sentinel-2 imagery were acquired for the area. And if I draw up the true color composite imagery, this is what it looks like on that day, the Sentinel imagery. And now I'm going to draw the false color composite imagery for the Sentinel-2 acquisition. Here it comes in. Patience here as it draws in. Again, repeating maybe some of what we learned with working with the HLS data before. The true color composite imagery draws in very fast, but the false color composite imagery is rendered a little bit slower than the true color composite imagery. And if we take a close look at this imagery, if we take a close look at this imagery in the context of the active fire detection data from VIIRS, you can see with the, if I turn off the active fire detection data, I have all of these areas that are easily visible in the shortwave infrared data that are resulting from the thermal activity, the lava and the eruption activity that's going on around the main part of the volcano here, and it's coming down the east slope, as well as all this activity that's easily seen coming down the west slope. So these are lava flows coming down from the main crater of the volcano. And so that's what we're seeing when we see those detections farther out to the west and also creeping down the east slope. And this is a good example of how you can use the HLS imagery, which is much higher spatial resolution than the VIIRS and MODIS imagery, to discern and determine maybe what is going on there on the ground and is the source of the thermal detected activity that you can see there. This wraps up my demonstration here today with the static thermal anomaly data, and I just wanted to say again that this current static thermal anomaly layer that we have in firms is a prototype layer. And needs more work and improvements, and the firms team is working on doing that, and we plan to release an updated static thermal anomalies layer in the future. Thank you.
Thank you very much, Brad, for that thorough demonstration of static thermal anomaly data in firms and its functionalities. It was great to get a tour of how to use it. In this next demonstration, Dylan will be showing us how to generate a firm's map key, how to visualize active fire information on a static graph and interactive map, and how to analyze that fire data. If we would like to replicate the demonstration provided by Dylan, please see the link to the GitHub, which can be found under part 2 of our training webpage, as well as a link on how to generate a map key. We'll make a recording of this demonstration available by tomorrow so you can go through the process at your own pace.
Amazing. Well, thank you for the more technical part of this training. Here is where you'll start for the coding portion. And this is a GitHub repository. There should have been more materials provided if you'd like to check out how it works and all, but it's pretty simple. First, you all need to go to the firm's website here, get an API key. When you come over here, you'll just click Get Map Key, put in your information, and click Get Map Key. You'll then get an email where the body looks something like this. This is just a demonstration key for the webinars that we do, but you'll take this key right up here at the top, and that will be your map key that you will need to use the notebook that is linked down here. To get to the notebook, all you have to do is hit Open in Colab here. This will take you over to Google Colab, and then you'll be able to make a copy and then do some work from there. So I'll take my API key. There's some API overview information and different information on our sources and all the different satellites that are available. But the code starts down here in the setup and authentication part. And then you'll take your API key, and where this big green bar is, you put it in between these two quotes. Once you've done that, this will enable, you'll click run, and then this will ask you if you'd like to connect to Google. It came from GitHub, so you can click run anyway. After that is done, it will connect to some server provided by Google, and it will import all of these packages that are used in this training. And you'll see setup complete API key is loaded. Then we can come down here to the world example. This function I wrote to query the firm's API for the world with all of the information on the different sources, day range, date string, all of the things like that. Pick play just to load this function. Once you load this function, you can pass the details into it. And we're looking at the world here for the date of August 20th in 2025 for the VIIRS NOAA 20 near real time data set. It'll print out exactly what API link you used here. You can click on that, and then it'll bring you into a new tab with the raw data itself. But this will load the data into a data frame from Pandas, and you can see an example of the first couple lines here, the information included below. There is all of these columns, and this little backslash is showing you that it's continued on the next line. So these are the rest of the columns. And now I'll move on to showing you a bounding box example. We'll need to run this to load the function so that it can be called in the next block. This bounding box is in the Amazon basin, and I prepared it ahead of time just so that everyone could get a quick example. Once you run this, it will show you the date of August 26th, 2025 for the data inside the bounding box. And then it will also print out an example of the data frame here, which is similar to the one above for the world. In this case, we're using the VIIRS SNPP satellite in the near real time. These are our available sources below with information on their real-time status, standard status, where they cover in the case of Landsat. And that just shows you how to get the data in a bounding box and a function to use that to pass the bounding box in. To ingest the data into a geodata frame from the firm's API with lat-long coordinates, we'll run this function that turns it into a geodata frame. Then we can run the data on the data frame area from the world example, which is up here. See how it's labeled data frame area. This will take in that data frame area and then turn it into a geodata frame. As example shown here with the points. You can do an exercise here to see how continue to do some coding and see the amount of or the number of points or active fire detections in this example with a confidence above 80. You can easily filter on the confidence, which does not look like there's one on the VIIRS SNPP satellite, but manipulating the function up here for a different source or calling it when you call the function itself, we'll be able to reveal some different confidence values. They're not available for all of our satellites for various reasons. But so that we can view some of these satellite detections, we're going to use the geodata frame and then a plot function in that so that we can show these active fire detections in the world for the same date of August 20th plus 1 day. So there's 2 days total. Once we run this, it will show the exact same plot that we were showing earlier, showing the world, and you can kind of make out Africa over here and North America into South America over here and Europe and Asia over here. This is a static plot, so you can't zoom in or click into it. However, we can use the folium map to show the same data on a interactive map so that we are able to zoom in and such and see different areas. In this case, it's colored by confidence. It's taking a little bit to run right now. Now that it's finished executing, we can scroll in the bottom box below the code and see the different parts of the map. We can zoom in or out, send that backwards, and take a look at the different fire detections based on confidence. And we can go into part of Brazil over here and see that it is colored in the way that we wanted it to be. All right. Moving on. We will now count fires by the day. So using the same data frame earlier on the acquisition date variable, we will convert it into date time and then create some group by date time or group by acquisition date and then the size of those acquisition dates. So it'll be the number of fire detections by the acquisition date. And then we can use PLT to plot the figure. Right now it's only showing 1 day. Go up and show. Let's go change this to 2 days. We will now do some manipulation based on the date, and you can do this for any of the different columns that are available in our output or additional data that you have brought in to do some subsetting or some charts on. So right now we're going to take the data frame and the acquisition date. We're going to turn it into a datetime object so that it can be grouped by the date. And the size in this case is the number of fire counts. I just showed this earlier, but now you can see that it went from 1 day to 2 days worth of data of August 20th and August 21st, showing that there was more fires on, or more active fire detections on August 21st in the world than there was on August 20th. As a conclusion, we set up authentication for the firm's API, retrieve data using the firm's API and bounding box queries, and for the world, ingested the data into pandas and geopandas, visualized the fire detections with the static and interactive maps, and then analyzed some temporal patterns. And that is just some basic manipulation of our firm's active fire detections using our API. You can expand this to historical trends over time, overlaying fire detections with different information that you may have about various things that have to do with land, such as land cover or population data sets. And you can also develop automated monitoring pipelines from things like this. Below is the homework section, which is where you'll be able to do all of the homework here below. And yeah, that's it for me. Thank you all for watching.
Great. Thank you very much, Dylan. And as I mentioned, we're going to make this recording available by tomorrow, so you can go through this on your own time. But let's summarize what we learned here today. First, Brad showed us how to access and use STAs in firms, which included the display of STA layers, how to display the STA feature source types, such as industrial heat sources or natural heat sources, and identify active fire detections associated with STAs. And we also saw how to access, ingest, and visualize firms' data using a Jupyter Notebook. And just to summarize this training series, this two-part training demonstrated to participants several new capabilities within firms. In part one, we looked at burned area mode in firms, new VIIRS burned area product, and the use of HLS imagery and indices to perform burned area assessments. This is useful as monitoring post-fire impacts to vegetation is essential for evaluating burn severity, which informs post-fire debris flow risk, understanding patterns of ecosystem recovery, and identifying areas required for restoration intervention. We also looked at smoke and aerosol mode in firms, the use of aerosol index and pyro-CB layers to identify and track wildfire smoke. And as we learned, wildfire smoke monitoring is critical for air quality and public health applications, as exposure to fine particulate matter within smoke can cause respiratory issues and other health complications. And then in part two today, we looked at static thermal anomaly information to identify satellite active fire detections that may be associated with industrial sources, and then also how to access, ingest, visualize, and manipulate firms' data using a Jupyter Notebook. Homework is available now on the training webpage. It'll be due on the 3rd of December. And for those who attended both live webinars and completed the homework by the deadline, you'll receive a certificate of completion via email approximately 2 months after the completion of this course. Here we've included the contact information for myself and today's speakers, as well as links to the ARSET website and YouTube channel. I would like to take another opportunity to acknowledge our fantastic guest presenters, Jenny Hewson, Brad Quayle, Dylan Mendez, Diane Davies, as well as Asen Radoff and Otmar Bolsina from the Firms team. Thank you very much for joining us on this training series. And now we'll move over to the question and answer session. We've been monitoring the Q&A box for questions, and we've been moving them over to this document. If you have future questions, please locate the three little dots on the lower right-hand side of the application or web browser for this WebEx, and you'll see a Q&A section. Please enter your questions there. But the ones that we have, we've tried to start answering. So we can start off with question number 1. What are the data we rely on for fire detection? Is it only thermal data or smoke, or is there any other data that helps to identify false positives, like wind congestion or accuracy metrics? I think I got the gist of what this question was asking.
Hey, Brock, this is Brad. I can take that question.
Oh, hey, Brad. Great to have you on.
Yeah, great question. The way the active fire detection works is it's reliant on thermal data or thermal detection of activity, and it can be affected by heavy cloud cover or heavy smoke cover, as is noted in response here. And the way it works is, when it identifies obvious, thermal activity, above average temperatures there in a given pixel, what it does is it slides into what we call a contextual analysis part of the algorithm, and it looks at neighboring or adjacent pixels to assess their thermal response in order to figure out what that pixel would look like in the absence of fire. And if we have a large enough departure there statistically from that thermal response based on the response of its neighbors, which are not also obvious fires, the algorithm can then determine with a certain level of confidence whether or not that's an active fire detection or not. And the second part of your question, as far as using information that can help you identify if there's potential false positives on the detection, you can use the confidence information that I mentioned. So like on the MODIS active fire detections, there's a confidence level that ranges between 0 and 100%. And with the VIIRS data, it's a categorical rating of low, moderate, or high confidence. And that those confidence levels are affected by where the detection is, like if it's adjacent to a water body or a cloud edge or whatnot, which may cause some confusion in the thermal response and determining those statistics that I mentioned before. So you could look at those confidence levels for an active fire detection and maybe consider excluding some of those very low confidence level detections, which may be actual false positives.
Great, thank you. And I put the link that you see right here to the firm's facts in the chat. Question number 2. How about aerosol layers? Is it possible to estimate spatial distribution? Have we ever used other satellites like Tempo or PACE to integrate into the results?
Hi, Brock. This is Jenny. I can take that one. So Firms currently makes available aerosol index layers from ONCS, which is aboard SMPP as well as NOAA 20. And this was covered last week by Diane in webinar 1. This set of aerosol index layers are useful for both the detection as well as the tracking of aerosols and aerosols from smoke from fires, as well as interestingly dust storms. And I also wanted to highlight that NASA's overarching near real-time system, which is called LANTS, and within which the FIRMS system is situated, continually investigates additional data sources that could be useful for a range of applications, including wildfires, for example, and has recently made available multiple near real-time products from ESA's Tropomi sensor, including an aerosol index product, as well as selected near real-time products from PACE. And we are currently working to make available selected near real-time tempo questions, which I know the questioner had specifically asked about. So I will provide the links for those as well, for the PACE one. Thank you.
Thank you very much. Yeah, so it sounds like you are already on top of a lot of this other data being integrated. Question 3, what is the definition of data ingestion? And I think this was asked during Dylan's demonstration near the end. Yeah, and the answer here, just a means of acquiring the data. Yeah, if there's a follow-up question from that participant, please let us know if there's more that you wanted to know. Question 4, another question, is it possible that firms captures temperature anomalies caused by other sources rather than fire? I saw areas on the map I know and suffer from urban heat islands by high levels of impermeable surfaces, such as asphalt or buildings.
Yeah, Brad here. I'm happy to take that. Yeah, that's another really good question. Yeah, the fire detection algorithms are used for MODIS and BEERS and the other sensors that are available in firms. They're designed to detect and measure thermal radiation that are at very elevated or high temperatures that are associated with combustion and fire and whatnot. So these types of thermal anomalies that you're describing here with urban heat islands and whatnot, they're just not designed to detect activity at that particular temperature and whatnot. In some cases, in some sensors, particular how should I say, its approaches have had to be taken to exclude those areas, so we don't end up getting false positives all over the place, like from urban heat islands and desert surfaces and whatnot. But yeah, the algorithms are designed to not capture those areas as thermal anomalies.
Great, thank you very much, Brad. It sounds like, yeah, the sensors aren't just designed for that particular detection. Question 5, I was wondering if the static thermal anomaly maps we saw on the firm's website are made available somewhere as shapefiles. I would be interested to use them to improve the maps I use to distinguish vegetation fires from non-vegetation fires in my own algorithm. And it looks like there's a start of an answer here.
Yes, I can take that one. So we do not distribute the static thermal anomalies layer, but the information tab, the little eye icon on the firm's website, gives you all the information about where we are getting our static thermal anomalies information from.
Okay, thank you very much. Question number 6. What sort of time intervals, I'm not sure with the WRT, I guess what kind of temporal resolution or flyer vacations are you working with your data? And I'm going to assume this is going to vary depending on what sensor or platform we're talking about.
Yeah, I can take that. There are various temporal sampling based on the satellite you're looking at. It's different for MODIS and different for BEERS, different for geostationary satellites all across the world. Our frequently asked questions would be the best place to find information about that, or in the information tab on whatever layer you are looking at.
Okay, great. Thank you very much. So find the layer and then you can find some information on how often that is being sampled. Thank you.
Yeah, and one more note, in our advanced mode, I think is where it is, there is orbit overpasses of the polar orbiting satellites, so MODIS and BEERS. That can help you identify when the satellite has overpassed your area or area of interest.
Oh, great. Thanks for pointing that out. If I remember correctly, the intro to firms earlier this year had a section where that was being displayed. Okay, I have a question I haven't moved over here yet, but I'm going to throw it in here so everybody can see it. What about solar farms? Is it possible that they will show a map like a false positive?
Yeah, Brad here. I can take that one, Brock. Yes, potentially solar farms can, due to sun glint, cause false positives in various active fire detection products. These polar orbiting active fire detection products, like from Modus and Veers, the NASA algorithms are very robust. They use additional bands in the visible and near infrared wavelengths to help identify those areas of sun glint and reject those false positives. So the Veers and Modus data are pretty good in rejecting or keeping those false positives out of the data. However, the geostationary active fire detection algorithms are not as quite as good as Modus and Veers in rejecting those, identifying and rejecting those false positives. So you would have a tendency to see those false positives from sun glint from solar farms showing up in the geostationary active fire detection data.
Thank you. I have another question here. Would STA detect peat fire in context of a below ground peat fire? And would it be obscured by heavy smoke from vegetation fire?
Yeah, I'll take that one again, Brock. The short answer would be generally no. We're trying to exclude these natural fire events or vegetation fires from the STA, and we're doing that by looking at persistence of the fire activity. For example, an industrial source would have detections, over a long period of time throughout the year, whereas a wildfire, peat fire or whatnot, would not be persistent throughout the year. So we're trying to exclude those areas, wildfires and whatnot, by looking at the persistence of those detections.
Great, thank you. Looks like there was a question in the chat. I'm not sure what the question was, but the answer from Jenny. There's been a lot of coverage of the pollution in India in the news that uses firms. Oh, I am from India and I have a yearly problem of farm fires that can contribute to pollution. How can we distinguish general fire from stubble burning through Veers or other NASA products?
Thanks, Brock. Sorry, I saw that question in the chat, so I just started answering it. So interestingly, there has been a lot of coverage of the pollution in India in various news sources, and firms are being used, data from firms are being used to help inform what is happening. And as far as can we distinguish general fire from stubble burning? So additional contextual information, so spatial extent of the farms, etc., could be used to further kind of refine the locations and potential sources of the fires. But these fires are certainly being captured by both VIAs aboard NOAA 20, SMPP, and NOAA 21, as well as by Modus aboard Terra and Aqua.
Great, thank you very much. I did see a question regarding to the homework. Once again, that link can be found under part 2 on the training webpage, and it is live right now. Question number 10. How does static thermal anomaly filter out thermal anomalies from industrial facilities? So it's more like, how does it work? Are they using coverage binding from some file or with the nearest neighbor algorithm. Can you tell us a little bit more about this feature? Looks like we have a link here. Some we put in the chat.
Yeah, Brock, I'll be happy to answer that. Yeah, as noted in the response there, we have an Earth Data article posted about the STA and how a general description of how they're derived. But as mentioned before in the demo, what we did is we took the cumulative active fire detections for at least SNPP VIRs over the course of the year, and also Terra and Aqua Modus. We used Modus primarily to take advantage of Terra's morning observation capabilities, and then we'd have Aqua and SNPP VIRs for the afternoon observations. And yeah, we identified those persist areas where there was persistent fire detection activity within, or I should say over, extended periods of time, again, looking at that persistence measure. And we're able to, identify those areas or locations as static thermal anomalies, which may be due to industrial heat sources or natural sources like volcanoes and whatnot, like as we discussed during the demo. We provide the sources of industrial heat activity in firms as a reference, because we're not trying to capture all industrial sources of heat out there on the landscape. We're just trying to capture the ones that are, or at least identify the ones that are routinely identified in the Modus and VIRS active fire detection products, and that helps users identify those particular detections that are associated with those features. Yeah, that's all pretty much have to say on that one, Brock.
Here's a question. Is there a way to delineate surface versus atmospheric thermal energy? Up here in Canada, we have large smoke columns that carry lots of heat and appear to artificially inflate the size of the fire. But once the smoke subsides, their hits are no longer valid. It often appears in a repeating grid pattern of hits along the direction the smoke column is heading. It looks like we're going to get back to you on that one. Look for this answer to be filled in, but we're going to consult our science team and get a little bit more of an accurate answer for you here.
Yeah, thanks, Brock. And just to note that, again, webinar 1 kind of touched on this, and so that would be another source of information, and as well as we will consult our science team and provide additional information.
Great, thank you very much. Okay, that seems to be the last question right now. We have a few minutes left before the top of the hour. So if anybody has any more questions, feel free to type them into the Q&A box. And as it comes to the homework, it's due by the 3rd of December. And then it's going to take a little bit of time for us to process attendance and homework submission. So typically, you can expect to see your certificate of completion sent to you as a PDF in your email about 2 months after today. In the meantime, this is an advanced training that builds off of one that we did earlier this year that was offered in English and Spanish. There are plans to deliver this in Spanish as well in the near future. So please look for that. If there's anything any of our guest speakers want to offer in general to the participants here today, I welcome you to do so.
Well, thanks, Brock. I would like to say thank you to everybody for participating, and we hope you found this information very useful.
Well, thank you very much. It's great to be back, and we thank everybody for hanging in there with us. and look for more wildland fire trainings to be offered by the ARSET program in the future. And have a great rest of your week, everybody. Thank you.